Hello, this is Professor Gabor. We're talking about Chapter 7, the Central Limit Theorem. And it has three sections: the Central Limit Theorem for sample means, the Central Limit Theorem for sums, they're very closely related, and then using the Central Limit Theorem. So this is one of the principles as we're moving from descriptive and statistics and probability into inferential statistics, where we're trying to use statistics to make decisions or judgments. The central limit theorem is critical to this because it says, suppose x is a random variable with a distribution that may be known or unknown. It can be basically any distribution. Using a subscript that matches the random variable, suppose that mu sub x is the mean of x, and sigma, the standard deviation, sub x is the standard deviation of x. Remember, x can be any distribution. Every distribution has a mean and standard deviation. You just use the formula to calculate it. That the fact that we're using Greek letters means that these are parameters of the population distribution. Well, we can't always look at the population, so we draw a sample of size n. So now as n increases, the random variable x bar, which is on that sample size of n, the statistic that estimates the parameter mu, the mean of the population, tends to have a normal distribution with the same mean as the population and a standard deviation. This is sub x. It's not standard deviation times x. It's this standard deviation x. Maybe we could actually fix that. No, we can't. Which tends to be it tends to be normally distributed. No matter what the underlying distribution, it can be any distribution. It can be discrete, it can be continuous, it can be uniform, it can be skewed, it can be bimodal, which means it has two humps instead of one like the normal distribution has. And as n increases, well, this is the magic part. As n increases, how big does n have to be before we can just assume it? Usually a rule of thumb that's used in quality management is you have a sample size of 30, you can pretty much assume that the x bar is going to have a normal distribution. We don't make inferences, therefore, on the individual items. We make inferences on the x bar because the x bar has a normal distribution. This is called a sampling distribution, a sample of size n. If we take the sample of size n and take the average every time, it will, and plot it, it will tend to have this kind of normal distribution. So if you keep drawing larger and larger samples, as opposed, such as rolling 1, 2, 5, and finally 10 die, and calculating their means, the sample means form their own normal distribution. This is, like we said, called the sampling distribution. The normal distribution has the same mean as the original distribution and a variance that equals, remember, variance is the standard deviation squared, that equals the original variance divided by the sample size. So variance is easier. If we went by variance instead of standard deviation, it's just the original variance, sigma squared divided by n. If we want the standard deviation, we take the square root of that. That's why you get sigma divided by the square root of n. To put it more formally, if you draw random samples of size n, the distribution of the random variable x bar, which is the sample of size n estimate of the parameter, the population parameter, which consists of samples mean, is called the sampling distribution of the mean, and that sampling distribution approaches a normal distribution as n, the sample size increases. You can also get a z-score for the x bar. X bar minus the mean of the population, if you know what it is, divided by the standard deviation, if you know what it is. So the flaw in all this is that you know what the mean of the of the parent population is, and you know what the standard deviation of the parent population is. Mu sub x is the average of both x and x bar. In other words, if I take several x bars and I take the average of all the x bars, I keep doing this experiment over and over again. I take samples of size n, and I calculate the mean, and I plot that distribution. The mean of those means, which is sometimes referred to as the x double bar, they put 2 bars on top of it, which means the mean of the means, has the same mu sub x as the population. Sigma times x bar, or sigma x divided by sigma sub x is really what it is, divided by n, is called the standard error of the mean. So here's a problem. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size n, 25, are drawn. Find the probability that the sample mean is between 85 and 92. Well, let x be one variable from the original known population. The probability question is asking you to find this for the sample mean. So the x bar equals the sample mean of size 25. Therefore, the mean of this new normal distribution is going to be mu sub x is 90. It's the same as the original population, but the standard deviation of this sampling population, or sampling distribution, is going to be 15, and n is 25. So since the original distribution, that's what they're saying here. Sorry. Mu sub x is 90, sigma sub x is 15, and n is 25. The x bar, the average on a sample size of 25, is going to have a normal distribution with 90 as the mean and 15 divided by the square root of 25. 15 divided by the square root of 25 is what? Is 5, and that equals, that should be 93. So you draw a graph. The graph looks like this. We want the in-between. So what's that probability? 6.995. Can we verify that? Sure we can. Let's go here, and let me make this smaller and readable. So we have population, mean, standard deviation, and we have n, which is the sample size. Okay, so what do we have for that? Now let's make this so we can bigger so we can see it. I'm sorry. Let's make this a little bit bigger. Okay. Okay, so now we can see it. This is the population. So we don't know the distribution. We know the mean is 90. We know the standard deviation is 15. We know the sample size is 25. So if we look at the sampling distribution, let's make this bold, and let's make it, yes, this maroon color. And then the sampling distribution. And let's wrap that text. And also make it the same color and bold. The mean is going to be equal to the same. Doesn't change, but the standard deviation is going to be equal to the original standard deviation divided by SQRT, which is square root of the sample size, 93. So now we want the probability that, so let's do it here, probability that and I can't remember what it was. So what are we saying? 85, X bar is between 85 and 92. 85 is less than X, let's call it X bar, like this, which means that I'm using a sampling distribution. I don't know what the parent distribution is anyway, to 92. That's an in-between. So I need what? I need to take the difference of the larger norm dot dist, comma, and then the X is going to be, in this case, 92, comma, 90, comma, 3, comma, 1, because we're always using CDF, and I subtract the lower one from it, which is what? Norm dot dist of, not 92 now, this time it's 85, comma, 90, comma, 3, standard deviation of the sampling distribution, and 1 for cumulative. And I get, let's take it to 4 decimal places, which seems to be standard, 6997. 6997, yay, we did it properly. You can do it on a calculator, but we're not using calculators. Here's another problem. In a recent study reported on October 29th, on the Flurry blog, the median age of tablet users is 34 years old. Suppose the standard deviation is 15 years. Take a sample of size 100. Notice that the sample sizes have nice square roots so far. That doesn't stay that way. What is the mean and standard deviation of the sample mean of tablet users? What does the distribution look like? Find the probability that the mean age is more than 30. Find the 95th percentile of the sample mean age to 1 decimal place. Okay, so we got this problem, example 7.3. This was example, I believe 7.1, not sure. Let's see. Yes, that was example 7.1. And now we're looking at example 7.3. And I want to do the same kind of thing here. Why don't I copy some of this? Let me copy these cells, because the problem setup is going to be the same. I have a population that has a mean of 34 years. Right now, we know what the population mean is. We're not going to know always here. And then we have, again, 15, and our sample size now is 100. So just by copying that, I've done all the calculations. My new, the mean of the sampling distribution of this population, of the averages on a sample of 100 is not still 34. But the standard deviation is much reduced. It's 15 divided by the square root of 10. Click there, you'll see 15 divided by squirt of 100, which gives me 1.5. Now, this is going to be this distribution here will be normal. It's going to have, so the answer to part A is normal with 34, comma 1.5, a standard deviation of 1.5. Or what's the mean of standard deviation? I guess this is part B. Part C says what? Find the probability that the mean age is more than 30 years. So we want to find here the probability that X bar is greater than 30. So that's a upper tail. So it's equal to 1 minus the CDF of the lower tail. So we have norm dot distribution. And what do we have? we want 30, that's the magic number there, comma 34, comma standard deviation 1.5, comma 1, boom, 0.996, 9962. What's part D asked for? It wants the 95th percentile. Well, we're at 99th percentile, so the 95th percentile is going to be somewhat less than 30. 95th, and then we'll call it percentile. I wrote it as a percent ILE. Well, now we have to use the inverse norm. So we're finding here now, and I think the inverse norm, not norm, I think the inverse norm maybe it's inverse dot norm. Maybe it's norm dot inverse. I don't know. I haven't done this in a while. And it gives you probability, mean, standard deviation. Well, the probability is going to be 0.95. The mean is going to be the same mean of the sampling distribution and the same standard deviation as sampling distribution. And we find that, and it says that at 36, the 95th percentile is at 36. And I'm sorry, I said this wrong. At 30, being greater than 30 was 99% of the distribution. But if we want it to 1 decimal place, there's the 1 decimal place, 36 and a half years old. And you could sketch this. I will put a pencil and paper version of this with just the Excel formulas and not the answers. You could look at this Excel spreadsheet for the answers. Okay. Now we go to the central limit theorem for sums. And really, I meant to have this slide first. So let me fix this. Now that slide is first. If we go back here where we were, example 6.3, let's go to central limit theorem for sum. Let's say x and y are two independent. Independent is the most important part. Normal distributions. And they have, it has a normal distribution mu of x and sigma sub x, and the y variable, the variable we're calling y, has a normal distribution with mu of y and a standard deviation of sub y. Then the distribution of their sums is as follows. It's still a normal distribution with a mean that is the sum of the two, and standard deviations are not additive. Variances are additive. So I have to square the standard deviations of x and y, add them together, and take the square root of them to get the standard deviation of the sum of x and y. This is a critical part. This is the critical and hard part of this. Variances are additive, standard deviations are not. Note the variances, standard deviation squares are addable, standard deviations are not. So we've got that. Now, the central limits theorem for sums is let's take x as a random variable with a distribution that may be known or unknown. It doesn't matter again. It can be any distribution. Mu sub x is the mean of x. Sigma sub x is the standard deviation of x. This is the population distribution. If you draw random samples of size n, then as n increases, the random variable, the sum of x added together n times to itself, will be normally distributed. It will be n, the mean will have n times the mu of x, and the standard deviation will be the square root of n times the standard deviation of x. So this time all the distributions are the same, and I'm just adding them up. So it becomes n mu x and square root of n sigma x. It's the same as, it's just a variant of the central limit theorem. So it says that if you keep drawing larger and larger samples, and the sum of x, well, let's take this. The sums form their own normal distribution which approaches the normal distribution as the sample size increases. The normal distribution has a mean equal to the original mean multiplied by the sample size, and the standard deviation equal to the original standard deviation multiplied by the square root. So the random variable sigma x has the following z-score associated with it. Well, we're not going to really calculate z-scores on this because, as you saw, both Excel allows us to put the standard deviations, the means and standard deviations in directly. The whole point of standard normal distributions was when I only had I could only get the probabilities from table. I had to convert everything to standard normal in order to use the table. I didn't have tables for every mean and every standard deviation. We used that empirical rule to find the equivalent probability of the standard normal distribution and apply it to the distribution with a mean that was different than 0 and a standard deviation that was different than 1. So here's example 7.5. Pretty simple. An unknown distribution has a mean of 90 and a standard deviation of 15. A sample size of 80 is drawn. Oops, 80 does not have a nice square root now. Is drawn randomly. Find the probability that the sum of the 80 values or the total of 80 values is more than 7,500. Find the sum that is 1.5 standard deviations above the mean of the sample. Well, let's go to Excel again. Example. And this is example what? 7.5. There's other examples we have obviously skipped. And I'm going to kind of do the same thing here. I'm going to copy this, but I'm not going to call it a sampling distribution this time. What am I going to call it? And let's make it so we can actually read it. There you go. You can easily see that now. And it was what? 90. And it was 15. And it was 80. This is so nice. But this is not going to be the case anymore. It's the sum. What do they call this? This is the right thing. The sum. Let's call it the sum distribution. Sum distribution. And in this case equals 80. So. We never left, right, justified those. So this is going to be, it said it's going to be equal to the same mean, but times, in this case, 80. So it's going to be 7,200, and the standard deviation is going to be the same, but times the square root of n. So the standard deviation is going to be equal to this times the square root, not divided by the square root, times the square root of n. So both the standard deviation, and let's take the standard deviation to maybe 2 decimal places. Now it asks a couple questions. A, the random variable has the following z-score associated. Well, we did that already, sorry. Find the probability that the sum of the 80 values, so let's call it sum x. We'll call it S sum x, or the total of the 80 values is more than 7,500. Well, that's going to be I guess I was making capitals, probability of sum x being greater than, what was it? Short-term memory being the first thing to go, 7,500. So let's put the answer over here. That way I don't have to resize all the columns. And this is going to be equal to norm dot dist of what? 75, or it's going to be 1 minus this, whatever I get for this. Sorry. 7,500, comma, 7,200, comma, 134, comma, 1. This is the cumulative distribution, that's the probability of it being less than 7,500. 7,500 is 300 bigger than the mean, which is at least 2 standard deviations, so this kind of makes sense. But I want 1 minus this because I'm doing the upper tail. 1 minus this. So I get a probability of 1, 2, 6, 7. And then what's my B question? What's my B question? Find the sum that is 1.5 standard deviations above the mean of the sums. Okay. Well, what is that? 1.5 standard deviations. So if I do this, my little x now is going to be equal to the mean plus 1.5 standard deviations times the standard deviation of this sum. So that's not what I want. There we go. So it's going to be 7402, 7401.2. So I want the sum of x to be this. So now I want the probability that sum of x is, find the sum that is, oh, they didn't, that's all they wanted. They didn't want any probability. Well, let's do a probability. Let's say find a probability that is less than 1.5. Less than 7401.2. Now this has got to be very confusing, right? So I think I should move this over here so we have all the answers in the same place. And then it should be equal to norm.dist. And since we're doing a lower tail, we're not asking for an upper tail. We don't have to subtract anything from 1. It's going to be that number, comma, 7,200, comma, 134.16, comma, 1, and that says we're at 93. 4 decimal places, 93.92. Good for us. Using the central limit theorem. Well, we have this law of large numbers. It says if you take samples of larger and larger sizes from any population, then the mean x bar of the sample tends to get closer to mu. From the central limit theorem, we know that as n gets larger and larger, the sample follows a normal distribution. The larger n gets, the smaller the standard deviation gets, which means that the sample mean must be close to the population mean on a large sample. We can say that mu is the value of the sample mean as n approaches larger. The central limit theorem illustrates this law of large numbers. So here's an example. A study involving stress is conducted among students on a college campus. The stress score follows a uniform distribution. The lowest stress score equals to 1, and the highest score equals to 5. So it's on a 1 to 5 scale, basically, and they made it didn't say if it's uniform discrete or uniform continuous, but I'm sure it's discrete if we're grading students on a 1 to 5 scale. So with the low score being a 1 and the highest score being a 5, using a sample of 75 students, find the probability that mean stress score for 75 students is less than 2. The 90th percentile for the mean stress score for the 75 students. The probability that the total of the stress scores is less than 200. The 90th percentile of the stress score for 75 students. Whoa. This is kind of intense that we have to do this. Example 7.8. Well, let's do it. And it doesn't matter what the underlying distribution is. Let's go to this, and this was example 7.8. Let's do that. Example 7.8. All right, so now we're doing both the sum and the sampling distribution, because it's asking questions about both. Mean stress score and 90th percentile stress score. So let's see what we got here. We go over here. Let me copy this over to sample example 7.8. Let's make it so we can read it. And what do we have? What's our mean? The probability. So it's a 1 to 5. We don't know what the. Do we know what the sample? It's a uniform distribution. Do we know what the mean and standard deviations are for that? We have to find that out. And then we have this other problem. And I'm going to end this quickly because I'll come back and do these and do these two problems in a separate video. So, but I want to get this out earlier. Here, example 7.9. Find using the central limit theorem to find a probability that the mean. Well, here we never did the second problem here. 7.9. The market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone. The analyst finds out that for those people who exceed the time included in their basic contract, the excess time follows an exponential distribution with a mean of 22 minutes. Consider a random sample of 80 customers who exceed the time limit. Let X be the excess used by an individual cell phone customer. So we know that X has an exponential distribution of 1 divided by 22. That's the rate. From previous chapters, we know that the mean is 22 and the sigma is 22. Let X be the mean excess time used by the sample, n equals 80. And we know that X bar has 22, has a mean of 22, and 22 divided by the square root of 80 by the central limit theorem. So then we can look at this problem, this example. Find the probability, blah, blah, that it's greater than 20. Suppose that one customer who exceeds the time limit for a cell phone contract is randomly selected. Find the probability that that individual customer's excess time is longer than 20 minutes. Explain why the probabilities in part A and B are different. All right. Like I said, I will solve both these problems in another shorter video also. But I want to say this. You're going to have a quiz on Tuesday. Class will be face-to-face. And the quiz will have 3 problems on it. Everybody must do the first 2 problems. It will have a problem like this example 7.1. It will have a problem very similar to 7.5. You have to do both of these. And then it will have a problem like example 7.9 if you want to get an A on the quiz. So the highest score, if you don't do the third problem that I'm going to give you, is like 85. So your grade will be on a total of 85. But if you want to get 100%, if you want to do better, if you want to get an A on the quiz, you have to do the third problem. I'm going to give you 20 minutes to do it. It's going to be open book, open notes. Okay? Thank you very much, and we'll talk to you soon.